The advent of the industrial Internet of Things has made it possible to revolutionize how maintenance is tackled within industry, moving from reactive to proactive maintenance. Large quantities of sensor data can now be collected, enabling, for instance, that these sensors can be installed on multi-purpose industrial vehicles, wind turbines, or solar panels, in order to measure a vast range of parameters. This collected data can serve to monitor the health of those assets and to predict its maintenance before imminent failures occur. Predictive maintenance is therefore of great interest for many companies, as it significantly reduces, for example, maintenance costs and unforeseen downtimes. This new concept is, however, not without challenges for those that want to implement it. Common problems related to predictive maintenance are about having precise and smart sensors available in order to collect data about a specific asset and environment, capturing qualitative data with sufficient resolution from various industrial assets, preliminary local pre-processing of the data, sensor fusion, and feature extraction in order to reduce the amount of data to be transferred, establishing robust wireless communication in challenging environments, enriching data collected from assets with the data from other sources, for example, weather data and historical data, cloud-based processing and fleet-based analytics for root cause analysis and failure prediction, providing only relevant information to the right people at the right time and in the right format to allow collaborative decision-making. 47 industrial and research partners across Europe joined forces in the Mantis project. Mantis is a European research and development project. Its objective is to realize a proactive maintenance service platform architecture based on cyber-physical systems. In this framework, the 3 Belgian partners, Sirris, Ilias Solutions, and 3E, were involved in the project and decided to focus their work on exploiting intelligent, data-driven technologies for failure detection and root cause analysis. In this video, we will show the work done and the results obtained within the Mantis project by the Belgian Consortium. Ilias Solutions is a Brussels-based software company. Their software collects information about the operational use of assets to drive the maintenance and logistics processes. They focus on customers with a large and diverse fleet of highly mobile and complex assets. 3E is an independent technology and consultancy company. 3E provides solutions as well as guidance to improve renewable energy system performance, to optimize energy consumption, and facilitate grid and power market interaction. Sirris is a private collective research center with about 2,500 member companies active in 13 technological sectors. Sirris's mission is to improve the competitiveness of its member companies through technology and innovation. The Sirris's data innovation team participates in the Mantis project and consists of highly qualified data science experts. They contribute to the project by sharing their extensive knowledge gained from various projects around predictive analytics. Ilias Solutions focuses on the off-road and special purpose vehicle use case. Today, data is collected manually and maintenance is still triggered based on fixed intervals for most of these assets. Factors that may have influenced wear of the asset or its components are not taken into account. In most cases, the operators of the equipment are not experts on the assets or experts in data science. The few tools they have available are either too specific to a vendor's equipment, making it hard to get an overview of the entire fleet, or too generic for data acquisition and machine learning to be of immediate use. Ilias Solutions' goal is to provide a pragmatic end-to-end predictive maintenance solution for a large and diverse fleet. They are improving their own custom-designed sensors. These sensors collect raw data, perform edge computing, and transport feature data over Ilias access points to a central analysis and decision-making environment. Their mathematical models determine how the equipment was used and calculate the impact on its wear to allow for more accurate predictions on the remaining useful life. The result is then presented in a user-friendly interface. By the end of the Mantis project, Ilias Solutions customers will have an end-to-end solution. Sensors to collect the data on their assets, infrastructure to transport the data in their challenging environment, a central data storage and analysis environment, and a user interface that provides oversight and insight on the fleet maintenance status. Ilias has access to different kinds of fleet asset data. Sirris's data innovation team's responsibility was to exploit such data to its full potential in order to achieve the business goal of Ilias. Their tasks were checking the data quality, because industrial data is always noisy due to sensor malfunction and communication errors. Identify and remove outliers, input missing data. Explore the data by visualizing and detecting structures. A final step is the data modeling by clustering and identifying different asset usage behavior. In the context of the Mantis project, the main objective of 3E is to focus on a use case that aims to improve the energy performance of photovoltaic plants by reducing their downtime. The downtime is reduced by applying root cause analysis and fault diagnosis and detection methods. Thereby, operation and maintenance scheduling will be improved, which in return will reduce maintenance costs. Plants' recurrent diagnostic is necessary to make them perform better at a good performance rate. A statistical analysis of 644 plants in 3E's monitoring service Synaptic showed that 25% of plants were performing less than 7% below expectation. To overcome this problem of underperformance, the PV Health Scan suite has been proposed. The use case answers to this main problem by checking the quality of the sensors in the park through the solar sensor check and the state of the park itself via the PV Health Scan. Through the solar sensor check, a thorough data quality check is performed to assess the health of on-site parameters. The PV Health Scan, on the other hand, shows the energy losses for the different loss types over the energy conversion chain, starting from the sun radiation to the energy metered at the AC connection busbar. Anomalies can be detected at component level. A degradation analysis of the components in the PV array is performed over the period of analysis. Computing loss analysis at different stages of the energy conversion system allows us to identify where and when unreasonably high losses occur and which components perform as expected. Additionally, an inverter maximum power point tracking analysis goes through a health check of the PV array inverter combination and helps to detect problems and perform maintenance on time. A detailed historical health and performance check diagnosis on the plant can be performed by retrieving information from Synaptic, pre-processing the data, and generating the features using the developed algorithms. An automatic report is then generated that goes through different chapters of the plant health analysis. By the end of the Mantis project, 3E will expand the use of the PV Health Scan in the Synaptic monitoring platform. Irradiation data is central in the definition of the performance ratio of a PV plant. The quality of the irradiation data can be influenced by several root causes, such as calibration errors or time-setting issues. 3E has manually set a number of indicators to decide whether or not the irradiation data may be flawed. Sirris's data innovation team's responsibility was to investigate these manually set thresholds to automate the decision process by going from a simple threshold check to a machine learning approach. Sirris performed exploratory data analytics. Using statistical and visual data exploration techniques, they observed some of the indicators computed by 3E have a seasonal dependency. An alarm threshold associated to that indicator should take that into account, or in other words, a single static alarm threshold for a seasonally dependent indicator will lead to more false positive or negative alarms. Except irradiation, the performance ratio calculation is also influenced by the losses in inverters and solar panels. Sirris's data innovation team responsibility was to analyze data and to propose a new model for current losses in order to improve final performance calculation of the PV plants. Characterizing conditions for higher than expected losses. They explored the health scan data of many different PV plants to identify current loss cases that are interesting to investigate further in more detail. They performed a systematic drill-down analysis of the data over its different dimensions, for example, location of the plant, inverter types installed, module types attached, portfolio owner, maintainer, etc. This allowed them to pinpoint particularly interesting cases, for example, inverter types that suffer from higher than expected current losses in particular locations when particular module types are attached.